This event has been made possible by ORTOP and the Southern Oregon Robotics League, SOAR. Special thanks to Trial and Terror 8372 for hosting this event at St. Mary's in Medford, Oregon. Live stream and media coverage provided by C4 Robotics, 9851. Matt Heverly is the supervisor for the Mobility and Mechanism Group at the NASA Jet Propulsion Lab and is a former Mars Curiosity rover driver. He's excited to speak about his experiences and this season's FTC challenge, Rover Ruckus.
Thank you guys very much for having me. I'm super excited to be able to chat with you guys today. And I just watched the game animation, and I'm pretty excited because it is very similar to what we have been doing for a very long time here at JPL. So we've been building Mars rovers for a while now, and this is our 3 generations of rovers that we've been working on. The first rover that we built was this little rover. It was about the size of a microwave oven. It was called Sojourner, and in 1997, it was the first rover to land on the surface of another planet. It didn't go that far. It didn't have a robot arm, so it wouldn't do well in your competition. But it did some amazing science and really paved the way for starting to make rovers to explore space. After we built Sojourner, we built twin rovers. We built Spirit and Opportunity. This is where we had one design. We built 2 rovers, and we sent them to opposite sides of the planet. And these rovers were both amazingly successful. They were only supposed to last 90 days. And Spirit lasted about 6 years, and Opportunity is actually still driving on Mars today. It's been 14 years since Opportunity landed, and it's still cruising around. It's in a tough spot right now because there's a global dust storm that right now is encompassing all of Mars. And as you can see, the rover is a solar-powered rover. So when it doesn't get sunlight, because the atmosphere is so thick with dust, the rover has been shutting down. So we haven't actually heard from the rover in about 2 months. It's kind of hunkering down during this dust storm. Now the dust is clearing, and we're hoping to be able to hear from Opportunity any day now. We listen every day, and when Opportunity wakes up, it'll call home. She'll let us know that she's okay, and then we'll continue on exploring with her. The other rover that we sent up recently is Curiosity. This is an amazing picture. The rover actually has a robot arm and takes selfies. So it reaches out with its arm and takes its own picture and sends it to us on Instagram. And this is actually a picture that it took of itself on Mars. This was back in July of this year. And I don't know if you can see, but up in the atmosphere, it's pretty dusty. These are not blue skies. These are red skies because there's so much red dust up in the atmosphere on Mars. About every 2 to 4 years, we see these global dust storms that encompass the whole planet. And our robots have to be robust to that. So these are the ones that we've been building. Curiosity's still driving around and exploring Mars. And now what we're working on is building the next generation of rovers. So our next rover is the Mars 2020 rover. It's not a very exciting name. Hopefully we'll come up with a better name soon. And it looks a lot like Curiosity. So we've tried to take advantage of some of the things that we've learned with Curiosity, and we've kind of iterated. So we've made it a little bit better in a few different ways. We've got better wheels. We've got a better robotic arm. We've got better cameras. And we've got all new science instruments. So in the past, our rovers had really been looking to understand if there was water on Mars and how Mars evolved as a planet. Mars 2020 is the first rover that we're sending to really look for evidence of life. So we are attempting to try and understand if we can see fossils of ancient bacteria from Mars. We're also doing some cool technology demonstrations. There'll be a helicopter, a robotic helicopter, that we will deploy from this rover that'll fly around. It's got an instrument that's going to try and make oxygen out of the Martian atmosphere so that if we send astronauts to Mars, they'll be able to breathe, which we think is kind of important. But really what Mars 2020 is going to do is it's going to collect samples. It's going to make some little test tubes. It's going to drill holes into the ground and put pieces of rock inside these little test tubes. And what we really want to do is we want to look at those rocks back on Earth. So the whole plan for what Mars 2020 is doing, it's going to drive and it's going to collect these samples. And then we're going to send another mission to the surface of Mars. And this mission is going to have a rocket on it, because we're going to also have a rover on this next mission. That rover, we call it the Fetch rover, is going to go fetch these samples and put it in the rocket on the surface of Mars. And then we're going to launch these samples in this rocket off of the surface of Mars, and it's going to orbit around the Earth. But then it doesn't have enough propellant to get all the way back to Earth. So we have to send an Earth return orbiter, another orbiter that's going to go orbit around Mars, and it's going to find that box full of rocks circling the Martian planet. And it's going to go grab that box full of rocks, put it in its own little payload bay, and bring it back to Earth. And then once it gets to Earth, it's going to be circling Earth, and then it has to put them in what we call the Earth entry vehicle. And that box full of rocks is going to have to come into the Earth's atmosphere and then be able to land safely in the desert. And then we can take those rocks and we can put them into our special facility that we're going to build here on Earth in order to really examine these rocks. And the reason we're making all this effort to be able to bring these rocks back to Earth is so that we can see if there were signs of ancient life on Mars. That the question that we're really trying to answer is, was there life ever anywhere else in the solar system other than Earth? The other thing that this mission's trying to do is it's paving the way for sending humans to Mars. One of these days, that's the ultimate objective, is to make humans a interplanetary species. So they're not just on Earth, but we can live and explore on other planets. And those are the challenges when you guys are done with college that will be waiting for you if you choose to become an engineer at NASA. You can start answering some of the most fundamental questions of humanity of, is there life somewhere else in the solar system? And starting to prepare humanity to become an interplanetary species. I think those are some amazing goals, and what it takes is engineers to do that work. And when I look at what you guys do in the First Tech Challenge, it is exactly like what we do at NASA as engineers. We do three main things. The first thing we do is we design something. And I'm hopeful that this is what you guys have been doing for the last couple hours. Every crazy idea that we come up with, lowering a rover from a sky crane, putting a laser on a rover to be able to study rocks, all those started as ideas on a whiteboard somewhere. Somebody said, hey, I know the way we should land a rover on Mars. Let's put it in a giant balloon, and then it'll bounce around on the surface. And then the balloon can open up and the rover can drive out. I mean, it sounded like a crazy idea, but that's exactly how we landed our first 3 rovers on Mars. After we do that design, then we build it. This is what our assembly facility looks like right now at JPL. This is the sky crane. This is the thing that's going to lower the Mars 2020 rover down onto the surface. All of those parts are parts that were designed by engineers and that were made by machinists, and then we're putting them all together and building our spacecraft. And the last thing we do is we have to test. And this is where we spend a huge amount of time. And my biggest piece of advice for FTC teams is to spend a lot of time testing. We spend almost as much time testing as we do designing and building combined. And the point is that not everything's going to work perfectly the first time. So you want to be able to test it and then iterate. So something's not going to work. But if you wait to test it to the very, very end, then you're not going to have any time to be able to go back and make it better. So we spend a lot of our effort, many years worth of a project, testing our rover to know what works, to know what doesn't, to know how to operate it once it gets on the surface of Mars. And I think that's the exact same thing that you guys should be doing. Build your robot early, build prototypes to see how these little components and these subsystems work so that you can understand what doesn't go well, and then you can iterate and make it better. So we do this design, build, and test. It's exactly the same process that you guys are doing. So I had another interesting question that somebody asked me the other day. They said, why do you like your job so much? And I came up with 3 main things of why I like my job. The first one is because it's really hard. I actually love my job because it's hard. When you're able to accomplish something that is challenging, that sense of success to me is addictive. I want to do it again and again. Because when you do something that's easy and it comes easily to you, it's fine. But when you have a real challenge in front of you, it is extremely gratifying to be able to solve that challenge. Now, the picture over here with the JPL engineers, this was on the 200th Martian day on the surface of Mars. And we had a problem with the rover's computer, and it wasn't talking to us. And we think that it automatically switched over to its backup computer, and we were all waiting to hear if it was going to call home. We didn't know if our rover was alive or dead. And the worried faces that I see on those JPL engineers are just like the worried faces I see on those TNT engineers over there, where it's a hard problem. Not everything is going to come easily. Not every time is going to be a success. But when you do get that success, it's going to mean a lot. The other reason I like my job is because I learn something new every single day. I was trying to think of a good example of this, and I learned so many things, but one of the things that I've learned recently is we've started looking at geckos. I never thought when I became an engineer that I would learn anything about geckos. But what we found out is that the reason geckos stick to walls is something called van der Waals forces. And it's not like a frog, it doesn't use suction because suction won't work in space. Frogs wouldn't work in space because there's no water to create the suction. But geckos do work in space because they work on a fundamentally different principle of these van der Waals forces. So what you can see in that picture there is my friend Aaron made a robot that was able to grip things in space with kind of like suction cups, but it's gecko adhesive grippers. So I learned all about geckos and how to turn gecko's toes into a robot. And I'm sure that the TNT team over here is learning a ton about their system right now, and they're going to go home at the end of this day, and they will have learned a lot by taking on these hard challenges. The last reason I like my job is because it's really fun. This is, I think, the TNT mobility team over here having a good time. And this is the Mars 2020 mobility team, the people that build the wheels and the suspension system and the actuators over here on the other side. They all went together to the beach to go camping, and they watched the InSight spacecraft as it launched off to Mars on Cinco de Mayo this year. And when you go through these hard challenges, and when you learn all these things, you will build bonds with the people around you. And to be able to go through those challenges and to have those failures and to have those successes with people who can share in those accomplishments and that you can call a friend at the end of the day, that's what makes it so fun. So I know you guys have a lot of challenges in front of you, but I know that you will feel this sense of accomplishment with people that you really care a lot about standing by your side as you're learning all these new things. So I hope you guys are able to have a wonderful season this year. I'm very excited to see all the rovers that you guys build. And thank you very much for having me here today. Ooh, when will we have our first manned mission to Mars? It's a really good question. Right now, we have a lot of technology to develop. So we need you guys, when you're done with your engineering degrees, to help develop some of that technology. So a lot of it's how do astronauts grow food on Mars? How do we make oxygen on Mars? We think we have a good step for that. The other thing is those astronauts probably are going to want to come home someday. So we need to be able to build rockets on Mars and make rocket fuel out of the Martian atmosphere, because we probably won't be able to take all the rocket fuel necessary and land it on the surface. So there's all these key technologies that we need to be able to develop. My hope is that by 2050, somewhere in that range, we will, so in our lifetimes, we will be able to have humans on Mars. But it's going to take a lot of engineering to get there. So we need all of you guys to help with all those engineering challenges. Yeah, so do we use the moon as a base? Yeah, there's lots of reasons for us to go back to the moon, and we are shifting a lot of our focus to go start looking at going back to the moon. So the first thing about the moon that makes it a good place to go is that astronauts, when they're in the space station, and us here on Earth, are shielded from a lot of radiation by the magnetic field that surrounds the Earth. Once we go outside of that magnetic field, now astronauts have to deal with this radiation environment. And we don't really understand how long exposure to that environment affects humans. So a lot of what we want to do, it's a 2-day trip to the moon, and it's a 9-month trip to Mars. So we want to send humans to the moon to kind of practice living out there in this deep space radiation environment. It's also a good place where we know that there's liquid, or not liquid water, but H2O in an ice form at the moon, where we can take that water and build rocket propellant. And the lunar gravity is so much lower than Earth's gravity that we can actually launch from the moon more effectively in order to get to Mars. So we are looking at using the moon as a lunar base. So a lot of engineering focus now on going back to the moon. And since it's been so long since we've been there, a lot of that engineering knowledge is lost of how we did that. There's not a lot of engineers around that worked on the Apollo missions, so we have to reinvent a lot of those things. So yeah, we will have an active focus of looking back at the moon. Thank you very much. So how do we command the rovers, and how long does it take from the time we enter a command to when the rover moves on Mars? So we can't use a joystick, and the reason we can't use a joystick is because Mars is so far away. It's usually between 5 and 20 minutes for the speed of light to go from Earth to Mars. So if my rover was driving towards a cliff and I hit the stop button, it would take between 5 and 20 minutes for the rover to receive that command and actually stop. So probably too late to keep it from driving over the cliff. So what we do every day is we send the rover a list of commands. We send it once in the morning to the rover. And we basically write a program every single day. And we say, your first command is drive forward a meter. And your next command is take a picture. And your next command is turn left 10 degrees. And then it receives this command set. And then it looks at the first line and it says, oh, I'm supposed to drive forward a meter. And then it drives forward a meter. It says, check, I did that. And the next one says, I'm supposed to take a picture. And then it takes its picture, check, I did that. And it executes those all in a sequence. And it does all the things we asked it to do. And at the end of the day, the rover will take all that data and it sends us the telemetry of how far did the motors actually turn, and that picture that you wanted to see, here it is. And it sends it back home to us here on Earth. And then the rover goes to sleep at night on Mars. It's very cold at night on Mars. And while the rover is sleeping at night, the engineers on Earth are building up the next set of commands for the next day. So every day we have to write a new program to command the rover to do something interesting. We have a bunch of scientists here on Earth that are helping us decide what are those interesting things that we might want to do. So that's the way that we command our rovers on Mars. So will we ever drive our rovers on Mars with a joystick, or will it always be send it commands every day? So Mars is always going to be that far away, so we're always going to have to deal with that time delay. The way that we will have a joystick is if we have astronauts on Mars, then my guess is they will use robots to do a lot of the things that they're going to need to do. Just like a tractor plows a field here on Earth, we're going to need to do that on Mars. And my guess is we will not have an astronaut jump up into a tractor. We will have a robot to do that. And the astronauts on Mars will command those robots. Now, for the moon, our delay is 6 seconds. It's still hard for a human to be able to use a joystick with a 6-second delay, but it has been done in the past. The Russians had rovers on the moon called the Lunokhod rovers, and they drove them with joysticks here on Earth. But it took a lot of training for those humans to push forward on their joystick and wait 6 seconds, and then the rover starts to move, and then they'd have to stop, knowing that by the time they stop, it's going to take about 6 seconds for the rover to actually stop. So this time delay is an interesting thing in the field of robotics. So do we teleoperate something, joystick it, or do we give it commands and have the rover autonomously do the things that we want it to do? Those are all really fun and interesting questions that roboticists have to solve. And we will always have to deal with that. And as we explore the outer planets, when we go to Europa, the time delay is going to be a couple of hours. So we won't even have that quick turnaround of 20 minutes. We will have to send the commands, and it'll take a couple of hours for it to reach our spacecrafts when we go further and further away. That nasty speed of light thing where we can't send things faster than that always causes trouble. When we look at Mars 2020 now, currently, it's about 800 people that are working to build that rover. We have people that are designing the wheels, and people that are designing the batteries and the science instruments and the cameras and the chassis and the software that drives the rover, and the software on the ground that we use to command the rover, and the scientists and everybody. So we have a really big team. When we look at the total number of people that worked on Curiosity, it was about 3,000 people that had some part in making that mission happen. And when you have a team that big, there's nobody that can oversee everything. You have to be able to trust your teammates so they can go off and do something, and that when it comes back together, it's going to work. But that's why we have to test things so much. Everybody's off doing their own thing. And then when it comes together, we have to test to make sure that, part A worked and part B worked, but is it going to work when part A come together with part B? So when you have these big teams, it really takes a lot of organization of those teams and a lot of good teamwork. And you guys are experiencing that, because I'm sure sometimes you feel like, if I were the only one working on this rover, I could do it all myself, and I could make it just the way I want it to be. But then you'd have to do everything, and there's no way that you would finish in time. So you have to trust your teammates that are developing software. Trust your teammates that are developing the drive system. Trust your teammates that are doing the arm that's going to grab the unobtainium, and make sure that you test it when it all comes back together. I think that is one of the biggest challenges, is when you have a problem that is so hard that one person can't solve that problem. Now you not only have those problems, those technical challenges that you have to solve, but you have the team that has to do it. And that communication, the kind of delegation of tasks, defining the interface of how these things are going to come together, those are all critical parts of engineering. And as you guys figure this out in these realms, in the FTC realm, those skills will translate directly to the jobs that you're going to have in the future. And when I interview somebody and we hire them, rarely am I concerned with their technical skills as the most important thing. It's more about everybody that's going to come work here is going to be smart and can learn things. It's, can you work together as a team? Because that's often the limiting factor. So if you can learn to not only be smart on your own, but leverage your strengths with the strengths of the rest of your team to accomplish something greater than the sum of the parts, those are the most important things that I look for when we're hiring engineers at NASA. I'll give another plug too, back to your similar statement at the very beginning. I work in the mechanical engineering section at JPL. We hire about 50 interns a year and co-ops. So when you're in college, and if you kind of want to come work for a summer, or sometimes colleges have co-op programs where you take a semester off and you come work for 6 months. We have a lot of people that come do that. It's a very good experience for you as the co-op and intern, because you get to work on some amazing projects. And it's great for us because people bring us new technologies. You're learning new things in school all the time that we haven't seen because we've been out of school for a while. So it's a really great relationship. And I encourage you guys all, if this is the career you want to pursue, reach out, find a way to do it all the time. You're doing it now with FTC. When you're off in college, find a way to do it there through clubs, through internships, through anything you can. The more experience you get in engineering, the better an engineer you'll be. So what are the ways of communicating with our rovers on Mars? So it is almost like sending an email. We actually write text commands. The command can be drive forward, and then there's an argument of how far do we want to drive forward. And I would put the argument of 1 meter or 10 meters or however far we want. And we are writing these commands and these texts. And then there's custom software on the rover that can read that message and then say, oh, I need to drive forward 1 meter. I will take that and I will decompose that into a command for this wheel and a command for this wheel and a command for this wheel. And it will do the low-level control that will move the robot around. So we transfer via kind of a message from Earth to Mars over radio frequency waves, and then it will receive that command, and the software on board will interpret that and tell the rover what that command means. And I think it will be similar to how you guys are going to program your rover for autonomous mode, except think about reprogramming your rover for autonomous mode every day. And that's very similar to what we're doing. So do we have to worry about security? We don't tell anybody the actual commands, so it's not actually drive forward. But there is some of that command text that we keep to us, and we don't want to expose to the rest of the world because we don't want other people to be able to control it. It's very complicated. You need giant antennas to be able to send this commands off to Mars. There's not a lot of people that have those giant antennas. So it's not something we are that worried about, but we also take kind of our necessary precautions to make sure that we only have trained operators that are able to command our robots to drive around.
Special thanks to Matt Heverly for giving this presentation live at the Rover Ruckus kickoff event in Medford, Oregon.